Okay, welcome to the class. Let's continue our journey into object detection and segmentation. So first, let's briefly review last lecture's material. So we have been discussing classification in the previous lectures, and then object detection and segmentation are also important tasks in computer vision, especially for autonomous driving, where you have a complex traffic scene and you need to put bounding boxes on the traffic participants and also classify the objects. So object detection contains object classification as a subtask. So in addition to placing bounding boxes on the objects, you also need to classify each bounding box contained object. So the challenges are multiple outputs, multiple types of outputs. That is, every bounding box may contain a different object and large input images, high dimensional millions of pixels, which implies heavy computation. So the idea of placing a bounding box and classifying the contained image in the bounding box can be formulated as a single machine learning problem with a loss function that's a weighted sum of the softmax loss for the classification task and the L2 regression loss for the bounding box prediction regression task. And then you have ground truth for both the bounding box that's given to you by some human annotator, as well as the class label given to you by the annotator. And then you can backpropagate the loss with gradient descent to train the neural network. So the loss really has two signals. One is classification, one is the bounding box regression. So the neural network must learn to handle both tasks simultaneously. So multi-object detection is a little bit challenging because you have the more objects you have in the picture, the more bounding boxes you have to draw. So this is the sliding window approach. You just slide a window top to left to right, top to bottom, and run this detector classifier for in each of the bounding box. Very straightforward. And then you try a different size bounding box, and then you try a different size, and until you cover the entire image with all possible sizes. So as you can see, this is a very computation-intensive process. So to alleviate this process, we leverage the conversion of fully connected layers into equivalent conv layer. So the key is that the filter has the same spatial dimension and depth as the input. Therefore, every filter produces a single output element. So if you design the filters this way, then the FC layer can be converted into an equivalent conv layer with two possible conversion rules. So this conversion does not change the computation at all. The computation is exactly the same, because the filter has the same size as the input, so there's no sliding motion, right? You can only fit it once, and then you try the next filter. So with this conversion, you can improve the computation efficiency of the sliding window approach. So here's the a traditional CNN with 3 conv layers and 2 FC layers followed by a softmax. If you convert these FC layers into conv layers, then you can improve the computation efficiency of the sliding window approach. So on the top, you have the converted fully convolutional network for computing a single softmax output of a 10-element vector. 1 by 1 by 10, that's the 10 probability values from the softmax. And if your input is 16 by 16 by 3, and you have stride 2, then you need to produce 4 softmax vectors. So if you perform the sequential sliding window approach, you slide the window in here, and then you move over 2 pixels to this position, and then you move over down 2 pixels to this position, and then to the right. You have 4 possible positions for the input, and then if you do it sequentially, say you run a top pipeline, top network on the 16 by 16 image 4 times, then your computation is 4 times your computation load, computation cost for a single CNN. So then it doesn't, you don't gain anything. So the trick is that you perform the 4 convolution neural network pipelines in parallel, so that all the overlapping parts are not redundantly computed. They are computed only once and reused for all the 4 CNNs. So in terms of the dimensions, if you perform the fully parallel implementation, the output for this stage is 12 by 12 by 16 instead of 10 by 10, and this guy is 6 by 6 by 16 instead of 5 by 5. So this process is a forward pass only once, whereas in the previous picture, in this sliding window picture, we are computing. If we do it sequentially, you have to repeat this top pipeline 4 times, versus this single time to compute 4 output softmax probability vectors in one pass. So this is where you gain in efficiency. And even for 28 by 28 by 3 input, you can use the same trick and perform a single pass forward and generate 8 by 8, 64 softmax vectors, each vector with 10 elements for the 10 possible output class labels. So this improves computation efficiency by reducing redundant computations between overlapping sliding windows. So if your sliding windows are not overlapping, so for example, if you have a 4 by 4 sliding window, you slide it this is one slide, another, then this operation won't save you anything, because the computation cost is the same as doing the 4 by 4 input CNN 4 times. But if you have the overlapping computation, 14 by 14 on the 16 by 16 image, then you do save a lot of computation due to the shared computation cost for the overlapping regions. Any questions? So the sliding window approach, even with that optimization, is still very computation intensive. So region proposals is the more recent and more state-of-the-art approach. So instead of exhaustively trying all possible bounding boxes over the entire image for all bounding box sizes, you use a heuristic algorithm to propose some possible regions based on some criteria, say a blob-like image regions. So if an image region is a large patch of featureless color, then it's likely not to contain any object. It's likely to be sky or something, or water. So if there's an object there, there's got to be some kind of feature, some kind of blob in there. So they design some heuristics to pick out the blob-like image regions that are likely to contain objects. So there's no learning, it's just a heuristic. So for example, in this image, the region proposal algorithm has proposed these boxes. So some of these are pretty good. So this one contains a dog, this one contains a cat, this one contains a flower. So some of these are not very good. So this is a part of a dog. So yeah, so it's a heuristic. So Rcn essentially is a two-stage algorithm. So first you run the heuristic to find a region of interest, which may be of different sizes and shapes, aspect ratios. So, and then you normalize them by warping each proposal into same size, because the CNN net has been designed with this input size. And then you run a CNN on each of the normalized image regions, and it produces a class label and a bounding box. So the bounding box is parameterized by 4 numbers. So you have a starting point given to you by the region proposal. And then you perform some kind of fine-tuning on this bounding box to transform it by translation and the scale transform. So parameterized by these two parameters, bx and by, tx ty is for the translation, and thtw is for the scale transform. So you solve the regression problem by training the network to predict these 4 numbers for each region of interest, plus a class label. So you solve a combined classification regression problem for each of the region of interest. So here's an example. This is called the slow Rcn because there will be subsequent work on fast Rcn. So so this is the 4. So this is 3 are positive results, and this is a negative box. And for each positive box, you predict a class label plus the 4 parameters for the bounding box. For the negative box, you only predict the class target as the background. So remember that it's supervised learning. So you always have ground truth for the bounding boxes and for class labels. And then for test time, you run the region proposal, resize each region of interest, and run the CNNs on each region, and use scores to select a subset of region proposals to output, and compare with the ground truth boxes. So here's the detection criteria. It's intersection over region. So blue is the ground truth, and red box is the your prediction result. So the larger the score, the better your prediction. The better is the regression task. So typically LU threshold can be set to be 0.5. So if you have 50% overlap, then it's a pretty good prediction. So non-maximal suppression is meant to remove redundant bounding boxes. So here we have the detector has output 4 bounding boxes, but actually some of them are very close to each other. So you want to actually output 2 bounding boxes. So by eliminating the non-max boxes, max here refers to the maximum classification score from the class label prediction. So among these two, the blue and the orange, you look at the prediction score 0.9, 0.8. So you keep the blue because it has a higher classification score of 0.9. And among these two, yellow and purple, you keep the box with the larger score of 0.75 versus 0.7. So you keep the bounding box with the more confident class label prediction, and throw away the rest. So in the end, you have these 2 bounding boxes left, both with pretty high confidence in the class prediction. Then we discussed the mean average precision, which is the a common metric for evaluating object detectors. So it's the average precision is the area under the PR curve, a precision recall curve. So recall the definition of precision and recall. So for each of the predicted bounding boxes, and you look at the ground truth boxes for dog, and then you rank all the dog detections sorted by the score, the probability from the softmax. So this prediction has 99.99 score. It's pretty high for predicting a dog. And then you look for LU higher than the threshold, say 0.5. So if you do find a match in LU, then you declare a true positive, a true positive equal 1. And then you look at the next highest dog detector in terms of a score, and you match it with the ground truth dog boxes. So there's another match. So TP is 2. And look at this predicted bounding box. It had a pretty high score of 0.9 for detecting dog, but it doesn't match any of the ground truth dog boxes. So any of the remaining ground truth dog boxes, because the first 2 has been matched with the predicted boxes already. So you can only match it to the remaining one. So there's no match because the LU does not exceed 0.5. So it's a false positive. And then you look through the next one, the score is pretty low, and there's no match. So another false positive. And finally, this one, it has a match with the remaining ground truth stock bounding box. So you have another true positive. So finally, you draw this precision recall curve, and it's shaped like this. So the larger the area in the PR curve, the better your detection result, your object detector. So so the ideal condition is when you have precision equals recall equals 1. So you hit all the ground truth boxes and have no false positive detections. So and then you have this shape of precision recall curve, and you have the area under the curve of 1. And then so that's for a single class. So the previous example is for the dog class, and then you do it for the cat, you do it for the car, and then you average the numbers to get the MAP value. And then to go further for COCO dataset, you try all possible thresholds and average them. So let's look at fast Rcnn. So the main difference is that now we have a ConvNet as a backbone network to extract feature maps from the whole image. So here's the slow. The slow is added later, the original version of Rcnn. So the region proposals are generated with a heuristic algorithm, and then you process each region of interest with a ConvNet. So contrast this to fast Rcnn. You put a backbone network, could be AlexNet, ResNet, VGG, one of the well-known networks, and this network is run over the whole image to extract the image features. So these are the image features. So this is the feature map. So, however, unlike the original, say AlexNet, you don't run the softmax on top of it. Instead, you only run the convolutional part to extract the feature maps, and then you run a region proposal heuristic to extract regions of interest, and you crop and resize the features to fit the next stage. The next stage, you run a lightweight per region network to perform bounding box regression and classification, which outputs a class label plus a bounding box. In fact, it's a box transform per region, the 4 parameters. So starting from the region proposal, you'll fine-tune the proposal to your final desired final prediction of bounding box. So the difference mainly lies in the where the region of interest, the region proposal algorithm is run. So for the slow Rcn, the original Rcn is run on the raw image, and then you have a pretty heavyweight ConvNet going through each region proposal, which is slow because you may have many region proposals, say 2,000. Whereas in this case, you run a backbone network only once through the whole image and generate the feature maps, and then you run region proposal on the feature maps, not on the raw input pixels. And then the next stage, you run the lightweight per region network, much smaller than AlexNet, than the network used in slow Rcnn. And then you produce because most of the hard work has been done by the backbone network. And these per region network can be very small to perform the last stages of classification and regression. So as opposed to running a heavyweight ConvNet many times for the slow Rcnn. So by placing most of the work in the backbone network, this saves work for overlapping region proposals compared to Rcnn. So suppose region proposals have many overlaps, then you are wasting a lot of heavyweight computation on the overlapped regions. Whereas for this guy, even though the region proposals in the feature maps may be overlapping, the per region networks are really lightweight, so it doesn't really matter much. What matters is that the backbone network is run only once over the raw input pixels, and that's what saves computation cost. So here's a Rcn training example. You have this input image, and you run the backbone CNN through it to get image features. So this picture is it's kind of it's not very accurate because these are the features from the CNN, not really the pixels. That's why it's shown kind of faded, but it's I mean, it's not the raw pixels, just to understand. And then you perform the per region network to perform the classification of dog, cat, and a bounding box regression. And similarly, for the negative boxes, there's no box target and only a class target of background. So this part looks pretty similar to Rcnn, but except that now you have a backbone CNN for the heavy lifting, for the heavy work of extracting features. And this is just a few very lightweight, small networks for the final classification and regression. So here are a few examples. So if you use AlexNet for detection as the backbone network, you take the 5 conv layers for the backbone and 2 FC layers for the per region network. So if you use ResNet, you can use the last stage, the last few conv layers plus FC layer as the per region network, and the rest as the backbone network. So it's, yes, James?
I have a question. Can you go back 2 slides, I think? One more. Yes. So I'm thinking when you look at the slow Rcnn, I think it looks a bit more straightforward because you already have the input, the raw pixels that you have for each region, and you run it through the network. I'm thinking for the fast Rcnn, since we're going to run the raw pixels through the first backbone, then how do we get the regions from the output of the first component?
Oh,
Like when you run the first, when you run it through the backbone network, then you have image features there. How do we do the extraction? Because they're going to be like convolutional feature maps, right?
yes. So so the region proposal method is another heuristic algorithm. So a feature map is really no different from the raw pixel in terms of the dimensions. So for example, the dimensions may be you know, n by n by 3. That's the input pixels, and then after the CNN layers, you may have m by m by d depth dimensions. So from the perspective of the proposal algorithm, it's just like an image, except these are all high-level features. So the region proposal algorithm is also not exactly the same. You need to design your heuristic to extract region of interest from the feature maps, not from the raw pixels. But the basic idea is the same. So you look for salient blob-like features that are likely to contain some interesting object.
Okay, thank you.
Yeah. So yeah, in the Rcnn slide, I mentioned that there can be I think it's 2000, a few thousand, yeah, roughly 2000 region proposals. So as you can imagine, for an image with 2000 proposals, each one with different sizes, many of them are overlapping with each other. So therefore, for the slow Rcn, you're really doing a lot of redundant work. Not shown in this picture. This picture shows the three regions are not very overlapping, but in general, you may be processing the same regions many times through the CNN, just as we discussed for the sliding window approach, except now we have overlapping proposals instead of overlapping windows. So this from this motivation of reducing the redundant computation, that's how Rcn is designed. Fast Rcn is designed, is to run a single backbone network only once through the raw pixels, and to avoid the this redundant computation. So here's the performance. So the Rcn has training time 84 hours. Fast Rcn is 8 hours. There's another one, SPP net, which I did not discuss in the middle. And test time, the Rcn is very slow because it's running roughly 2000 CNNs forward passes over the single input image. Whereas fast Rcn is much faster. So, however, if you look at the breakdown of the running time, so most time is spent on the region proposals, and only a little time is spent on the if you exclude the region proposals. That is, you only count the CNN's computation time. So and then the faster Rcn is proposed to predict proposals from feature maps generated by the backbone network. The rest is the same as a fast Rcn. So now you have a two-stage object detector. So here's the backbone network, AlexNet, ResNet, whatever. You run it once per image, and you have a region proposal network to generate the proposals. And then in the second stage, for each region, you crop the features, a region of interest, and predict the object class and predict bounding box offset. So the difference now is that instead of the hand-designed region proposal heuristic, you make the network learn the region proposal network. So you train a region proposal network. So now you have two stages. One is the backbone network plus region proposal network, run only once per image. And then the next stage is the a lightweight region-specific network, region local network, to predict the bounding boxes and classification label. So region proposal network predicts the binary prediction, perform binary prediction for each anchor box. So here's the input image, and first you run the backbone network to get the features aligned to the input image. So this is shown as a faded image, but it's really the features. So suppose the input image is 640 by 480 color image, and the features are this size, 512 by 20 by 15. So that's a 20 by 15 spatial size and 512 feature maps. And then you the network you predict a false or true for each anchor box. So the red ones are predicted false, contains no object, and are discarded. The green anchor box, this guy, is predicted true, contains an object, and survives. So this prediction is simple logistic regression. So logistic regression is a special case of the softmax. So softmax is for generating a vector of probabilities for multi-classes. But if you only have two classes, then softmax turns into logistic regression. You can show the math for it. So here, because it's a binary prediction problem, we use logistic regression to predict a true or false for each of the anchor boxes. So each anchor box has the same fixed size at each point in the feature map. So that's the classification part. So it determines, predicts whether the anchor is an object. And then you perform, you also have a regression for predicting a regression, predicting the box that's a better fitting for the object. which better fitting is defined by higher IOU with the ground truth bounding box, which you transform from the green into the yellow box for each of the positive predicted boxes. So yeah, so that is the region proposal network. And so now this is another point is that previously we said we put an anchor box at every single position in the image, but actually we put K anchor boxes centered at each position in the feature map, each with different sizes and aspect ratios. So here we have three possible three bounding boxes. Here we have 2. So this allows or 4. We'll have 4 in here. So this allows a better fitting anchor boxes, which helps ease the downstream bounding box regression task and detect multiple objects centered at the same position. So for example, if the bounding box anchor box center is this black dot, then you may have 2 objects centered at the same position, the woman and the car. So you need to have multiple bounding anchor boxes to accurately capture the 2 objects. So this is the amount, the number of predictions you have to make. So here the image feature is 20 by 15 size with 512 feature maps. And then for each of the position, you place 4 bounding boxes, k equal 4. So that's 20 by 15 times 4 classifications you have to make. And 20 by 15 times 4k 16 regression parameters you have to predict, you have to train. So this is for training time, and then at test time, you sort all the these boxes, k times 20 by 15 boxes by their score, classification score, and take the top around 300 as our region proposals. So these are the boxes that are likely to contain an object. So if the score is very low, then it's likely not to contain an object because it's not confident that this object is there. So take the top ranking bounding boxes sorted by score and output them at the region proposals. So here's the training process for faster Rcnn. So for stage 1, you run the backbone CNN to output feature maps, and then you run the region proposal network to predict the object or not, binary prediction, yes or no. And for each anchor box, as well as regression from the anchor to object bounding box. If the is a negative box, then you have no target for the bounding box, only a target for the class label of background, just like before. The stage 2, when you are training the network for producing the final class prediction and bounding box, you only run them through the proposals that came out of the region proposal network rather than searching. So other than that, the rest is the same as the fast Rcnn. So you crop the features to the same size for each proposal and use them to predict the class and box targets per region. So now the box target is the softmax output, dog, cat, background. Whereas for the region proposal network, it's logistic regression for binary classification, object or no object, or background. So yeah. So this slide is very important. So now you have 4 losses. The first is the Rpn proposal network classification loss, a binary object or no object. And you have the Rpn regression loss for predicting transform from an anchor box to proposal box. And then you have object classification loss for classifying each proposal as background or object class, dog, cat. And then you have object regression loss for predicting transform from region proposal box to object box. So it's a 2-stage system because you start from the anchor boxes, you generate region proposals, and then from region proposals, you generate object boxes. So in fact, the slow Rcn and the fast Rcn are all, as well as faster Rcn are all 2-stage networks. So except now we are training the whole entire system, the both stages all have trainable parameters. Whereas before, in the slow Rcn and fast Rcn, we have a heuristic region proposal algorithm running either on the raw pixels or around on the feature maps. Now we have gotten rid of the handcrafted algorithm and let the machine learning do all the job for us. So every step is learned, not hand designed. So here's the performance. We have very fast speed for faster Rcn due to the region proposal network being much faster than the heuristic region proposal algorithm. So that's the 2-stage methods. Before we, I think let's finish this part before we take a break. So So the single stage object detection, we do everything in one stage. So as in faster Rcnn, we had the first stage is a binary classification, object, non-object. So instead of that, we classify each anchor into C+1 classes. C is the regular object classes, 1 is the background. So, and also we perform regression of the bounding boxes to transform from anchor box to object box directly. There's no more proposal box. So this is the single stage method. So single stage detector classify each object as one of C categories or background. So suppose the feature size is 20 by 15, then you have 4K times 20 times 15 parameters to train for the box transforms for regression, and this many parameters to train for the classification labels. So there are K anchors at each position in the image feature map. So yeah, this is the number of targets we need to train for. So that's 4K numbers, box center and box width and height. And this is number of class labels we have to train for. So for each of the anchor box center, you have K anchor boxes, and for each K, you have a C+1 possible classes. So this is a single stage method. So summary, for slow Rcnn, you first run the region proposal algorithm heuristic on the image and run the CNN independently for each region. And the fast Rcnn, you perform one forward pass on the backbone network and then run the region proposal algorithm on the extracted feature map from the backbone network. And then run the lightweight per region network to extract the final bounding box and class prediction. For faster Rcnn, you perform the region proposal with another CNN, region proposal network, instead of using a heuristic algorithm. And then finally, for single stage, we simply perform the whole end-to-end in one step. So by one step, I mean there's a single stage. There's no more separate stage on each region of interest. So compare these two. So this is two stage because this is one stage, CNN plus RPN, and this is the second stage. Whereas single stage means that there's no more second stage. This is the only stage. And the targets are different. So instead of the binary classification, object or non-object, as in faster Rcnn, we directly predict the classification label, dog or cat, and also the final bounding box regression, the exact, the final locations and sizes of the bounding boxes. So if you have heard of this YOLO, you only look once, it's a pretty typical, it's a very popular one-stage method. So any questions?
I have a question.
Sure.
Will you have any lab session for object detection?
No, we don't. I thought about it, but all these methods are very computation intensive. So it's difficult to give a lab session. So I decided not to give one.
Okay, thank you.
Yeah.
I have a question here. What is the performance comparison between the single stage and the fast Rcnn? I think there should be some trade-off for single stage, right?
So I think a single stage is the most popular these days in terms of computation performance and the classification regression performance. So, I mean, does faster Rcn have any benefits? I'm not exactly sure. Let me see. This is 2017 result. So SSD is another single stage method. So this is the MAP, mean average precision we discussed before. Higher is better.
I think it says the two-stage methods, they get better accuracy, but are slower.
Oh, yeah. So it says here, two-stage faster Rcnn, fast Rcnn. Single stage feature extraction. So this is the using different backbone networks for feature extraction. So the yellow circle is inception, ResNet, and so on, VGG. And SSD. So SSD is somewhere down here. Faster Rcn is all the way up here. Horizontal axis is computation cost. So yeah, it's a very good chart, but it's a little bit out of date. So indeed, the circles, those two-stage methods have pretty high accuracy in terms of MAP, but they have pretty heavy computation, relatively heavy computation. Whereas single stage methods, this SSD here is a little bit low in the MAP score, but also less computation. So that's the trade-off. And also the choice of backbone is important. So you may choose a heavier backbone or lighter backbone. So that also implies performance accuracy trade-offs. Okay, Carla, you want to say something?
Yes, I had a little question because this YOLO is really nice, but it was kind of secret, at least last year when I looked at it. Is it kind of open source nowadays, or is it still secret?
YOLO, I'm not sure.
And there are like version 5 and so on now?
State-of-the-art MAP of 57%. I guess this is the newest, latest chart.
Yeah.
Yeah, it looks like YOLO wins in accuracy and cost on the COCO, so it's pretty good. So pre-trained model is available in darknet.
Okay.
I
will have a look myself. I'm just curious if you happen to know. But they were a little bit secret of how they did and so on. No? Top open source, yeah. Because you can download and run.
YOLO.
Sorry?
There is a GitHub project, I think, for YOLO.
Okay.
If you go down, yeah, YOLO GitHub.
Yep. Yeah, this is the old version, but anyhow, it's could be nice anyhow.
I think there is a YOLO version 5, but that is as a different developer from the original one.
Yeah, I'm just curious because it looked very useful for.
Pre-trained model, run the detector.
So I guess it might be compiled code also, so it's not like Python or something.
Yeah, I think this company or this person has this latest state-of-the-art YOLO model that's pre-trained, whereas many other people have developed their open source versions of YOLO, which may not be state-of-the-art in terms of performance. So here has a top open source YOLO project. So many people developed, I guess, third-party developers did this development. Yeah.
Yeah, which can be good anyhow, or good enough at least. So
yeah,
to play around with it.
Okay, let's take a break.
Thanks a lot. Yeah.
Okay, let's continue. So we have finished object detection. We discussed a regression, a progression of different detectors, starting from the original Rcn to fast Rcn to faster Rcn to single stage SSD and YOLO detectors. So in the slow Rcn and fast Rcn, you always have this handwritten part, the region proposal method. So region of interest from a region proposal method. Whereas starting from faster Rcn, you get rid of the handwritten part and let everything be trained. So this is kind of a trend in software development, whereas a traditional software developer writes a lot of code by hand, designs the algorithms by hand. Whereas today in the machine learning age, you just design neural networks and train the networks, train their weights and biases instead of hand design the algorithms. So it's so-called software 2.0, whereas you are turning away from hand coding more to the automatic training. So this was not possible or not popular before when computing power and data were not sufficient. But with today's big data and large computers, this becomes possible. So the job of the programmer is gradually turning more to the GPUs. Yeah. Yes?
Yeah, I have a question regarding, so what kind of algorithm is used in the autonomous vehicles for object detection?
So generally, these two are really out of date, a little bit out of date. So these are state of the art. So faster Rcn or YOLO or SSD. In autonomous vehicles, I'm not really sure in the commercial products. I guess both of these two should be fine. Yeah.
Okay, thank you.
And from the YOLO's website, so it seems that there's no trade-off in computation cost and efficiency. So from the figure, YOLO wins in computation inference time and in accuracy. So it wins in two aspects. So there's no trade-off for YOLO 3, I guess. Yeah, at least from the figure.
It feels like they advertise a little bit.
Yeah.
Exaggerate the performance, but it's okay.
Yeah.
I have a question. On the x-axis, you have time in milliseconds. Let's say in a self-driving, it's much, isn't it?
Oh, let me see. A few hundred milliseconds. Is that too much?
A human reaction is like 30, 40 milliseconds, but the vision system is much slower.
So my understanding, all the methods to the right, you can't use them in a self-driving car because they are much too slow.
Yeah, I guess, yeah. So look at the frame per second. So for YOLO and SSD, the single stage method, you can achieve 46 to 244 frames per second. Whereas for the others, it's only 8 or lower frames per second. And there's smaller versions of YOLO. Yeah, I would say that's true, but I guess it also depends on the hardware platform. I wonder what hardware they used.
But I think if you compare to humans, they are much slower than these detectors. Like if we see something, if we can react subconsciously, then we maybe do it in 100 milliseconds. But if you need to think, it will take several seconds, I guess.
Yeah, so here it says the numbers seem to be based on a CPU, but with a GPU it could be much faster. Yeah, I'm not sure what the numbers here. Yeah, this is yeah, pretty slow. It's 2017, I guess. I need to double check on the hardware platform. In this case, a few hundred milliseconds is definitely too slow for self-driving cars. So let's move on to the second part of segmentation. So this is an example segmentation, semantic segmentation for a self-driving car scene: the road, the buildings, the trees, pedestrian. Yeah. So semantic segmentation is to label each pixel in the image with a class label: cat, grass, trees. So do not differentiate among multiple instances. So here you have 2 cows, but only 1 cow label. There's no cow 1, cow 2. So in the earlier approach is sliding windows. Sliding windows is no longer used for either detection or segmentation due to its slow performance. But nonetheless, we introduce it. So slide a window across the image and apply a CNN to classify each crop's center pixel. So center pixel and give it a class label of cow, grass. So it's very inefficient. So you can use a fully convolutional network to perform segmentation. So the input is a height, width, and color image, 3 color channels. Prediction is height, width, the same size as the input. So the conv layers do not change the feature map sizes. Remember, we discussed same padding in the lecture on CNNs. So if you add the appropriate padding, then you can keep the feature maps the same size before and after the convolution. And finally, after a series of conv stages, you get h times w softmax and vectors. Each vector has c elements. So that's c times h times w scores. And then you take the max of the scores for each pixel as your segmentation result. So the loss function is per pixel cross entropy loss. So you're essentially making a decision for every pixel, which class this pixel belongs to, which class this pixel should have the label for. And you're making the predictions for all the pixels all at once. So the first problem is that the receptive field size grows linearly in the feed-forward direction with a number of conv layers, and convolution of high-resolution images without downsampling is expensive. So in the traditional, we discussed the design for CNNs. Typically, you have the typical design pattern for CNN is that you have a larger feature map sizes, but a smaller number of channels. But as you gradually go through the layers, you have smaller feature maps, but more and more channels, more depths in your feature map volume. So finally, you have a classifier. But for segmentation, you do not shrink the feature map size as in regular classification. Instead, you keep it constant, same size, all the way to the end, and make a prediction for every pixel. So this is a CNN that performed downsampling followed by upsampling. So it's another architecture. So the downsampling, you can use a pooling or stratified convolution. Both can reduce the feature map size. So you first reduce it by half, then reduce it even more, and then you upscale it to half and to the original size. So this architecture of downsampling followed by upsampling is more advantageous because it allows the effective receptive field size to grow more quickly in the forward direction, and also leads to more efficient computation. So receptive field, if you recall, is so this layer's neuron is looking at a particular region of the input. So this is a neuron. This is the region of the input. So so if you have multiple layers, then the receptive field for this layer is this. For the next layer, it's larger receptive field. For the next layer, it grows larger. So so with this architecture of downsampling followed by upsampling, the receptive field grows faster in the forward direction. So then it's faster than the previous constant size over all the layers. So the upsampling is done with interpolation or transposed convolution to get the output with the same size as input. I think this one is a typo. This should be h over 8, w over 8. I'll go fix it. So yeah, over 2, over 4, over 8. Yeah. Yeah, James?
I'm curious, for a segmentation problem, what does the ground truth looks like? Is it like each color, each pixel have a color, or how do we know that during training?
Oh, it's human labor. So you hire a lot of people from Amazon Mechanical Turk and label all the images with the pixel labels. Yeah, maybe you can have some tools to help the labeler, but he has you know, he has to draw some boundaries, and maybe, and then after he draws the boundaries, he marks cow for this region. So that's your ground truth. Human
okay.
labels, yeah. So, yeah, indeed. That's why for object detection and segmentation, the labeling cost is much higher than classification. Because classification labels, you know, you hire someone, he looks at it, it's a cat, it's a cow, right? It's easy for the labeler. But for this, you need to draw this thing with your mouse, and you need to, you know, it's really labor intensive. So it's very costly to get the labels. The figure shows the upsampling from a 2x2 into a 4x4 image with a number of channels. So you can either insert zeros, say you keep it in the upper left corner and insert zeros at other positions, or you duplicate elements like this. So the first is a bed of nails. It means that, you know, if you draw this on this three-dimensional coordinate, you know, most of the space is flat with zeros with a few non-zero points. So kind of like a bed of nails. And the duplicating elements, it means that, you know, the nearest neighbors have the same number. So another method is bilinear bicubic interpolation. So on the left is bilinear interpolation. On the right is bicubic. So this one corresponds to this one. This 2 corresponds to this 2. 3 is here. 4 is here. And then you can imagine inserting these 2 points, and the spacing should be uniform. So this point is 3.25. I guess it's not exactly uniform. So yeah, 3.75. So in the middle, so anyway, this is a more, it's a smoother form of interpolation. Whereas in here, it's less smooth. So you can see that there's a pretty large jump between the regions in the nearest neighbor, and pretty large jump between the zero elements and non-zero elements in bed of nails. Whereas in the interpolation-based method, the whole surface is smoother if you draw it in the 3D space. So remember we had a max pooling where we reduce we downsample the dimensions by taking the max elements 5, 6, 7, 8. The max unpooling is just the opposite. So you insert zeros and keep the max elements, except now you remember the positions of the max elements from before, from the max pooling step, and then keep the max elements in the positions. So yeah, these are the 4 positions for the 4 quadrants. And after you do a lot of processing, you place each of the elements in the original old positions to try to keep consistent with the input. So pair each downsampling layer with the upsampling layer. So this is the original convolution operation. So if you have a 3x3 convolution with a strat of 2 and path of 1, input is 4x4, the output is 2x2. So this is one element. The red box generates this red element. The blue box generates this blue element, and so on. And then you move down. So this is the other, generates this element. And this box convolution generates this element. So this is the material we covered in the lecture on CNNs. So transposed convolution is for upsampling, to generate a larger image or feature map from a smaller one. So if you have a 3x3 convolution transposed with a strat of 2, you apply the wave filter and copy it to the output. So, and whenever you have overlaps, you sum the elements. So for every pixel in the input, you generate output with the red box, and for this pixel, the blue pixel, you apply the filter to generate the blue box, and this is moving over 1 pixel, and in the output you move over 2 pixels. So for the overlapping region, you sum up the elements. And after you have processed all the 2x2 input input pixels, I call it pixels, but it's really the feature elements in the feature map. So you perform this and you sum up the overlapping regions to get the final 4x4. So this is really the reverse of the regular convolution. So here's the yeah.
Can I just ask a question for
Sure.
when you copy over when you're copying over the values? So in this case, will the first row of the output, will the top 2 both be the red value, and then they're copied to each output box, and then in the blue one it'll be just the blue ones, and then on where it overlaps it'll add them, but the rest are all copied over, so they're not doubled, but I mean repeated.
Rest are so what do you mean by copying what over? So this
what's the convolutional output? So the input, you have 4 values, right?
Let's look at this example. This is a one-dimensional example. Maybe it'll make things clearer. So.
Oh, is that just the filter? My bad. Okay. I think I understand.
Okay. So this is the 1D transposed convolution. So this is the input. This is the filter. And you apply the filter by multiplying A with XYZ. This is the output. Then you multiply B by XYZ to get another output. And then you have a strata of 2. So there's a 2-pixel offset between these two outputs, output vectors. And then you sum up the overlapped areas.
Okay, thanks.
Yeah. So the 2-dimensional case is pretty much the same, except in 2D. So this method generates a size 2 from a size 2 input to a size 5 output. In this case, so it's upsampling. So the filter moves at a slower pace than with unit stride. So if you had a traditional convolution unit stride, then you're moving at a unit pace. But here the filter moves at a fractional pace because the output elements are overlapping. So it moves slower than unit stride. So there's many names like transposed convolution, deconvolution, upconvolution, fractionally strided convolution, and so on. But this name is the most common name. Yeah, the reason we invent this new convolution method is that we want to do upsampling because in the CNN lecture, we discussed the same padding and different padding methods. So you can either reduce the dimension, the spatial size, or keep it the same. So you cannot increase the spatial size, but transposed convolution is designed to increase the spatial size for segmentation tasks. So we have discussed the semantic segmentation, but there are other variants of segmentation. So first, in computer vision, we distinguish between things and stuff. So things are object categories that can be separated into object instances, like cat, cart, or person. Stuff are the categories that cannot be separated into instances, like sky, grass, water, trees. So object detection detects individual object instances, but only gives a bounding box for things, whereas semantic segmentation labels all the pixels but merges instances. So here is a single cow label for the 2 cows. So instance segmentation goes further. You detect all the object instances and label the pixels that belong to each object. So here we have a cow 1 and cow 2 with different colors indicated. So the approach is to perform object detection, then predict a semantic segmentation mask for each object. And panoptic segmentation. So in addition to instance segmentation, we also label the pixels that belong to each thing. So cow number 1, cow number 2. Whereas for instance segmentation, we draw the each object in different regions, but give them the same label. So here's using mask Rcnn for instance segmentation. So this is an extension of the two-stage faster Rcnn detector extension is extremely simple. You just add additional head for mask prediction. The rest is just a faster Rcnn. So this allows you to perform instance segmentation by predicting a mask, which is irregular shape, not a box, and comparing it to ground truth. Then you have additional loss in here. So this loss is used for predicting the mask, in addition to the bounding box and class labels. And the magic of backpropagation will train the network to give you correct mask prediction. So here's some examples. So so this is the target mask for class chair in the bounding box. So yeah, this is a target segmentation mask for class person in the bounding box. So roughly looks correct. And then in the mask Rcnn, you first have the CNN plus region proposal network to get a bunch of region proposals, and you do the ROI alignment to put each ROI regional interest into the same size, 14 by 14 by 256 as the number of channels. And you perform the classification and regression for the object detection, and then you have additional conv layers this is additional head for predicting a mask for each of the C classes. So so this is these two are the targets. So these two are obtained by human labelers, and then the prediction and this mask, you formulate a L2 loss function and do backpropagation. So you can play more tricks based on this faster Rcnn. You add additional head, a key point prediction head, to perform a joint instance segmentation and pose estimation. So key points are the say humans left, right shoulder, elbow, wrist, hip, knee, ankle. These are the key points. So by adding this key point prediction head and with the ground truth labels, you again obtain another loss function term and backpropagate. So this is the prediction result for a baseball swing. So the idea is pretty general. So you just add additional per region heads to faster or mask Rcnn to perform additional tasks. So the per region heads receives the features after region ROI pooling and ROI alignment, and makes some prediction per region. So by adding these additional heads, you obtain additional loss function losses from the loss functions. If you have a loss function, you can backpropagate and train the neural network. So that's the end of the segmentation class. Okay, any questions?
So object tracking, what kind of algorithms are used for that?
Oh, so I didn't discuss it due to lack of time. Object tracking requires, so all the stuff I talked about is to process each single image. So for a classification, for segmentation, object detection, everything is a single feed-forward neural network from a single image. That is, you're not aware of the history. So whereas for tracking, you need to be aware of the past time steps to keep track of an object. So then you need to really treat it as a video, not individual picture frames.
So some kind of recurrent neural network is used also with that, or?
Yes, Rcn is used, is popular for tracking. The traditional, so before deep learning, the tracking was done by optical flow and traditional computer vision methods. But after deep learning, there are different approaches. One is Rcn to keep track of the history, including the more sophisticated versions of RSTM and GRU for instead of the plain Rcn we discussed before. Or you can use CNN by stacking multiple frames into one stack. Say if you want to keep track of a history of frames, say each frame has 3 color channels. If you want to keep track of 10 frames, then you just stack them together to form a 30 channels with the same spatial size. And then you perform the tracking task on the stack of frames. This also allows you to take into account history. So there are different methods, which I did not have time to, I do not have lecture time to discuss them. Yeah.
Okay, got it. Thank you very much.
Sure. So Friday is the due date. How are things going?
One point from my side is from Jupyter Notebook, if we want to convert it to PDF, that doesn't really look very good, the report. Is that a problem?
How do you do it? From the browser, did you do a print, or how do you do it?
Yeah, from browser, if I try to do the export to PDF, I think that doesn't work because then I was executing the Jupyter command line command. So it's kind of, there is a command called Jupyter NB convert that I Python NB to PDF. That converts it.
Does that work well?
Yeah, I think it uses LaTeX behind the scene. So you need to have the local LaTeX installed. But the quality is not so great, I think. I think that's,
Okay.
yeah.
From my experience, I find that if you do a print, it's pretty good. But if you do a save as PDF, it's not as good. Did you do a print?
I tried print from Colab, and it didn't really do good because the code blocks, some were really not in the same page, and it didn't really convert it in a nice way. With the command lines tool, it does it better, but still it's not so good. But I think that should be, I mean, my question is if formatting is important for the report or.
No, it's not. You know, it's okay if the formatting is messed up.
Okay, thank you. I mean,
Yeah.
it's not so bad. It's just with Word, probably I could do it better than this automatic one.
I think you can use just a link to the file, or what are the specifications?
But for a link, often you don't have permission, right? Can you grant permission to everyone from your? But I think it's more convenient for the grader to look at look at the PDF.
Yeah, sure.
Yeah, and you can grant permission. You just like Adu did. So then the advantage for the grader is that they can test run it if they want, but I guess they don't have the time to run many.
Yeah, you should send in. You should upload the IPython notebook so the grader can run them, and also a PDF. Okay, so I look forward to I have received I think 2 or 3 submissions, so I look forward to receiving your submissions. I hope everyone can finish in time. If a lot of people cannot finish, you know, I'll think about it. Maybe a few days of extension, not too much. Okay.
I think it's 4 submissions anyhow.
Okay, that's good.
There is some hope. It's a long way to 92 or something. So I hope it shouldn't be so difficult with all this help, but it is a little bit complicated, of course.
Yeah. So for the lectures, I'm gonna flip the order again. I'm gonna talk about control before planning. So the reason is for the programming assignment. I want you to get started on the PID control assignment pretty soon. So I'll talk about control next lecture.
And then someday I'm going to talk about reinforcement learning as well.
Yes, after planning and control, we go into reinforcement learning, which I think most of you are very interested in.
At least one of us. So do you have any idea what date that will be? Are those lectures, are they single 2 hours, or are they?
Oh, these 2 lectures should be finished in either 2 days or 3 days of lectures. So the week after the next, we should go into reinforcement learning.
Yeah, so somewhere like 10th of May or so. Yeah.
Yeah.
To know. So I will also prepare some exercises for those. I'm now working with some research. I tried to buy a graphical board from NVIDIA. It's really very difficult to find one. So, and then the administration at the department is not helping much.
But you have a GPU computer already, right?
Yeah, but they are not allowed to be run in a server. You know, if you have the 2080 Ti boards. But there were some new boards from NVIDIA arrived 2 weeks ago. They're called RTX A5000 or so. And they can be run in a server, so other people can access them. So if you have a lab, or in this case Trafikverket, the government, so they can try and run things. So that is nice. But maybe I steal one from your computer some night.
Yeah. Is it because all the Bitcoin miners?
Yeah, yeah, that's right. I sold my private card. Could sell it really expensive, but not the same as I bought it with. But I bought it like 3 years ago for 6,500 crowns, and I sold it for 3,500 after using it for 3 years. So So it was Bitcoiner miners. Yeah.
Yeah.
So yeah, sorry for the mess. Oh.
Okay, so I guess we'll finish it today. Tack för idag. Goodbye.
Tack som gav.
Ja.
Tack, hej då.